Good morning, good afternoon, all distinguished participants of the webinar. First of all, I would like to say thank you, ISA Secretariat, for organization of this webinar and invitation. In my presentation, I would like to draw your attention for approximately 10 minutes to look at my quick review of the sum of technological approaches toward future seabed mining and mineral processing. The beginning of deep-sea mining. Consortium AMCO, collector vehicle inside Hughes Glomar Explorer during the sea test in Pacific Ocean in 1976. Flexible link and buffer are located above the collector chassis, having very unique Archimedes screw drive. Mining technology early development starting in 70s. Attach here a scheme from late 80s, the scheme of collector. Mining platform vessel equipped with wind turbines, artificial ocean harbor for transport vessels, and steep vertical mining column and the collector. At this slide you will find a simplified overall structure of mining system. And here is an example of the mining ship conceptual design of interocean metal. And here is the current example of the technological approach towards future seabed mining. It's project Blue Nodules. It started 1st February 2016 and ended 31 July 2020. Supported with 8 million euro funds and consists of 14 partners from 9 European Union countries. Developed a new highly automated and technologically sustainable deep-sea mining system for the harvesting of polymetallic nodules from the seafloor. The key objectives of Blue Nodules were an industrially viable polymetallic nodule business case at water depth of 3,000 to 6,000 meters. In situ processing, sediment separation and sizing, and onboard process, dewatering and conditioning, excellent intrinsically safe working conditions, minimum environmental impact, and compliance with the relevant policies and regulations. Side event with the presentation of this project took place at stakeholder workshop was organized at the ISA headquarters in Kingston during July 2019 session. Newest example of the latest projects, Nowak Marine. Nowak Marine was established with a mission to develop and implement unique technological innovations for the maritime industry in the field of underwater propulsion systems inspired by biomimetics. Innovative data collection services for the marine environment to significantly reduce the cost of sea and ocean exploration costs in the near future. Patania 2 is the pre-prototype seafloor nodule collector built by Global Sea Mineral Resources. GSR is the Deep Sea Exploratory Division of the DEME Group. GSR commenced its technical development program in 2012. In 2017, the company tested a robot with a tracked propulsion system designed to crawl across the deep seafloor. It was Patania 1. Using the learnings about trafficability and maneuverability from this test, GSR engineered Patania 2, a 12-meter long, 4-meter wide, 4.5-meter high, 25-ton nodule collecting robot, also on Caterpillar trucks. Patania 2 is equipped with the latest cameras and sensors, including environmental sensors. The robot is controlled from the surface vessel via a 5-kilometer-long cable that provides power and communication capabilities. For the Patania 2 trial, GSR collaborated with the European research project Mining Impact. Scientists from 28 European institutes joined efforts with the German exploration contract holder, BGA, to independently monitor the trial to help understand the environmental effects of collecting mineral resources from the seafloor. Their research will also be made public in the due course. Now a few words about mineral processing. At this slide you will find examples of cooperation of ESA contractor with number of institutions in scope of the mineral processing of polymetallic nodules. 3 years ago, between 3rd and 6th September 2018, conference took place in Warsaw organized by ESA and Ministry of Environment. Processing technologies, metal recoveries and economic feasibility of deep sea mining. The workshop focused on the following core areas: processing technologies, metal recovery, economic feasibility of mining seabed, minerals, impact of seabed mining on terrestrial mineral supplies, environment, clean marine technology, waste disposal and recycling, international cooperation, regulations, and role of the ESA as regulator. The detail of this interesting meeting, including presentations, you will find at ESA website, link at the bottom of this slide. Polymetallic nodules have been recognized as a potential source of base metals such as copper, nickel, cobalt, mangan. However, the leaching and other processing methods of polymetallic nodules is complex and difficult due to their amorphous structure and the presence of metals as oxide and hydroxide form. In the present slide, 3 technologies for the recovery of base metals, nickel, cobalt, copper and mangan from manganese nodules from the Clarion-Clipperton fracture zone of the Pacific Ocean are presented. They were developed by research teams of the Interocean Metal Joint Organization. Technology 1. Hydrometallurgical technology of selective dissolving of polymetallic nodules using sulfur dioxide. Technology 2. A combined pyrohydrometallurgical technology for processing polymetallic nodules, including reduction of non-ferrous metals with coke or smelting into electric furnace with producing of polymetallic alloy. Technology 3, hydrometallurgical technology for processing of polymetallic nodules into autoclave by pressure sulfuric acid leaching using reducing agents, molasses, and pyrite. It was found that the choice of the technology for scaling up from laboratory tests to possible pilot plant experiments, it is necessary to compare not only the efficiency of the result, but also to conduct the deep economic analysis, taking into account the possibilities for performance, the actual prices of metals, environmental pollution, and other factors. Final remarks. Continuously, the prospects for deep-sea mining are improving. The metals in polymetallic marine minerals are crucial for a wide variety of emerging and traditional technologies. Several mining tests and environmental studies were conducted by some contractors and international consortia up so far, proving the technological feasibility. Technology transfer from offshore oil and gas is an additional factor since these industries have a lot of experience and the technology used is already developed and applied in very similar environments. Strong progress in ultra-deep water drilling, high-performing technologies and equipment can be adapted and converted towards deep-sea mining. System integration over a wide range of subsystem disciplines and processes across the entire value chain is one of the key success factors for deep-sea mining project. New technological solutions, as example global internet access, growing demand for clean zero-emission solution, hydrogen production will support growing deep-sea mining industry. Thank you very much for your attention.